Good afternoon. So in the last few lectures, we took a detour right, from stochastic processes to look at the center manifold reduction, which gave us a systematic way of deriving approximate models for the slow dynamics in a system while accounting for, in a consistent way, the influence of the faster variables. So generally, in many problems, right, and we looked at the specific example of Taylor-Harris dispersion in the last class, right, you have some degrees of freedom that evolve slowly and others that evolve faster. And if this time scale separation is enough, right, what happens effectively is the system collapses to some lower dimensional subspace, what we are calling a slow manifold. And all the fast variables evolve so quickly that effectively they are slaved in some sense to the slow variables. And that relationship between the fast and the slow, in other words, the fast, you can account for the way the fast evolves by saying that they evolve only through their dependence on the slow variables. Okay? And that dependence is what is the slow manifold, right, the functional relationship. So for example, if you are in 2D, x and y is fast, then writing y as a function of x describes some curve. Right? And that is the curve on which all trajectories collapse rapidly and then evolve right, until they reach their final state. So this is true for any system with dissipative dynamics. That means the fast variables are constantly relaxing. Okay, so whenever you have friction and so on, or diffusion, for example, in Taylor-Harris, the high frequency Fourier modes, if you think of it that way, right, the higher frequencies in the problem will get rapidly smeared out by diffusion. That just means that they are collapsing on the lower, slower manifold where the evolution is, where the spatial distribution is smooth. It can be constant, right, in the case when you have simple no flux boundaries in a reaction slab, right, or it can have some other shape. For example, in the Taylor-Harris problem, it has some kind of approximately parabolic shape, the underlying concentration distribution to which things are converging rapidly. So our goal is to find that, right, and that the center manifold technique allows us to find this thing. And once you know how the fast variables depend on the slow, in the equations for the slow variables, you simply replace the fast variables by their slow manifold approximation. Okay, so then you will get a closed equation only in terms of x or in terms of the slow variables. So we saw that in the PDE setup for Taylor-Harris, and we saw how from the PDE model where concentration varies in the r direction, right, in the r direction and in the x direction, right, where r diffusion rapidly homogenizes or brings things to some simple form in r. Right. Along x you have the slow advection. That is the main reason things are evolving in time. Okay. And so we saw how we can average out the r direction, which just means whatever is happening in r is fast, so you can effectively average it out and get an equation only for the concentration cross-section averaged, right, along x. And that happened to be this kind of Taylor-Harris dispersion model where you have advection with the mean velocity profile, but an effective diffusion, which is the dispersion. Okay, so now we are going to see, today we are going to return back to stochastic processes, okay, and see how all of that machinery can be used to address an important question which we had stopped with, right, when we were thinking about stochastic systems last, right, which is that if I now take an ODE system and put in a fast rapid forcing and take the white noise limit, I get Statanovich is what I said in one dimension. And I showed you an example of geometric Brownian motion, right, where I took an ODE, dx dt is equal to x into some function f of t. I made this f of t some rapidly fluctuating function but smooth. And we did this using a random Fourier series where we put some cutoff on the frequency. That inverse of that cutoff frequency is the small time scale. So as I take the number of frequencies that I have in my Fourier signal to infinity, I will approach the white noise limit. So we did this exercise and we saw that as we made the forcing function fluctuate more and more rapidly, we started getting behavior that looked like geometric random motion or geometric Brownian motion, but in the Statanovich interpretation. Okay, so that was what we did in a few classes ago, right, using this, I think we used a Jupyter notebook, right, to see this. So that was some kind of motivation, right, that we do get the Statanovich limit if you start taking a correlated noisy process and taking the white noise. But today we are going to prove this, right, for one dimension, and then look at later whether this holds also in multi-dimensions or whether there are more nuances. Okay. Fine, so let's first start by formulating what we mean more precisely about starting with an ODE that is being randomly forced but in a correlated way so that it still remains an ODE, and how one can, in a well-defined way, get the white noise limit. So let's just say white noise limit is our overall topic. Okay. And what we're going to start with is looking at an ODE that is being forced with some correlated. So we have some variable x, okay, which whose evolution we are going to model. So E of x is the deterministic part of its evolution. And b is some coefficient which then multiplies a forcing function zeta of t with a subscript epsilon. Okay. Because this stuff I'm going to say is some, you can think of it as my smooth random noise that one can generate with a sum of Fourier modes with random coefficients, right, as I had shown you in some classes ago. Right, so it's some function, okay, which is random in the sense that it evolves randomly in time, but it is, as of now, having a finite correlation. So it is not white noise. Okay. And epsilon is a parameter which, as I take to 0, I want to get the white noise limit. So for any epsilon not equal to 0, this is just a normal ODE with some forcing function you created. Okay. It's random in the sense that if I've generated this function zeta of t by sampling some random numbers. Okay. So I can solve x, I'll get one trajectory for one realization of zeta. I can always get another realization of zeta, I'll get another trajectory, and you can treat x then, x is a stochastic random variable, okay, for which you can get many trajectories. So you can do many simulations and so on. What we're interested in is seeing analytically, right, whether if I take epsilon to 0, how can I rewrite this term, right? When this becomes white noise, will this become an SD? Okay, and of what form? Right? Because if B doesn't depend on X, this is not as crucial. When B depends on X, I have to decide if I replace zeta with the Wiener process increments, how should this multiplication be treated, right? Is it Ito, is it Stratonovich? That is the question. Okay, so for the moment, let's just look at this zeta of epsilon. Okay, and I'm going to say that okay, I want to make zeta of epsilon t approach white noise as epsilon goes to 0. So remember what in this kind of Langevin equation framework, right, which we had started with originally, right, when we did this Brownian motions. So Langevin wrote something like this, right, where he treated the force as some zeta, which was white noise, right. So in this way of writing it, which is of course not rigorous, right, it's some kind of singular thing. This white noise has a singular behavior where, if you remember, it's delta correlated in time, and at the same time instant its variance is infinity. Okay, so we want to create that sort of situation when as epsilon goes to 0. So what we will do is say that epsilon of t is directly related to some well-behaved stochastic process, which I'm going to call alpha. Okay, so if I want to think about it, if I look at the correlation function, so I'm looking at zeta of t, zeta of 0, the correlation function at different times. So if it is white noise, it will be like a spike, right? It will be a spike, everything is 0. It's delta correlated, right? But at 0, zeta epsilon at 0. So what I would like is, if epsilon is finite, I have something like this. Okay, and then it becomes sharper and sharper. Okay, it will become sharper. You can't see it behind the board, but I guess you get the idea, right? So it will shrink as epsilon goes to 0. Right? So I have some smoothly decaying function for some finite epsilon, right? And this will roughly set the correlation time. And then as epsilon tends to 0, while maintaining the integral, it will shrink towards 0 and become a Dirac delta. Okay, so that's what I want to create. So one way of doing it is to, of course, I can take any kind of shape to start with, as long I'm anyway going to collapse it. So that kind of normalized shape is going to sit in some other stochastic process, which is well defined. I'm going to call that alpha. Okay. And to allow that control, I'm going to write it as such. Okay, where now if I do this, if I look at the correlation of this process alpha, it's something nice. Okay. Okay, so you can think of, suppose I have alpha of t is some well-behaved stochastic process. Okay, if I look at its autocorrelation, it will have some nice behavior. It will decay as time goes to 0, it becomes uncorrelated. And if I integrate this weighted by time, I'll get the correlation time. So roughly that is set by how quickly it decays, right? So it has some finite correlation time. And now what I'm doing is I'm taking this function, right, this kind of alpha, and I'm rescaling the time by dividing by epsilon squared. So now you see as epsilon goes to 0, suppose you take a point here, right? Instead of the argument being this time, it is that time divided by epsilon squared. So it will get pushed out. Or in other words, this whole thing will start to shrink, right, by just replacing the argument t by epsilon squared. Right? So any finite value of t as epsilon goes to 0 will be sent off to infinity. Right? So this entire function, which will be non-zero, will shrink closer and closer towards the origin. Okay. But if this peak is kept the same, it will just become 0. Right? So if I just write it like this, as epsilon goes to 0, I'm just going to have zeta being 0. Right? So I'll have no effect of this thing. In other words, if I take some stochastic process and I make it decorrelate, right? If I take its effective behavior, it will just become 0 because it will just average it. The only way to compensate for that is to increase the magnitude. Okay, so by putting this 1 by epsilon here, I am making this thing rise up effectively, so that I get a Dirac delta in the end. Why is this epsilon and this epsilon square? This again relates to the fact that we have to take a root t behavior when we divide. Right? Remember, we saw this right in the beginning when we did a simple Euler integration of random motion. We saw it again when we tried to construct this kind of smooth random function using Fourier modes. We had to divide by something that was like root t. Right? So we are doing the same thing here. If I say epsilon square is like the ratio of time scales, right? When epsilon is 1, my random function is on the same time scale as with x evolves according to a. Right? So without the noise, x will evolve because of a. That has some time scale. Relative to that, this epsilon square sets the relative time scale of the fast fluctuating process. If epsilon is 1, they are both same, I cannot do any separation. Okay? But my whole point is, as the random process is fluctuating very, very fast compared to the slow dynamics, right, then I can get some limit. So that's what I'm doing here. Okay. So to make this formal, we will say that alpha is such that its autocorrelation is some function g of t. So this thing is basically g of t. And of course, we would like the mean of alpha to be 0. Again, we are trying to go to the white noise limit, right, which has 0 mean. Okay, and so this is the autocorrelation function. And I basically want to say that the time scale is finite from this thing, right? So I'm going to require that if I integrate this g of t, so this function, right, if I integrate it out, so the area under the curve is basically something finite. So I'm going to call that d, we'll use it later, actually 2d, okay, because what we will see is we will naturally be interested later on in the autocorrelation starting from 0 to infinity, which we will call t. Okay, so if I do minus infinity plus infinity, I'll get 2d. Okay, the reason this is, I can write it as 2d is because basically it is obvious. Okay. So what I'm trying to do now is essentially say that I'm writing zeta as some rescaled version of some nice stochastic process which has a finite correlation time. A way of saying that is, if you look at the autocorrelation, it has a decaying function which has a finite area. I'm going to call that area d, okay? But not just, this is at 0, right? So the integral 0 to infinity I'm going to call d. Now I'm just making the following point, which will be useful later, that if I think of it from minus infinity to plus infinity, it has a nice symmetric property, this autocorrelation. Because clearly, if I look at g of t, which is, this is just g. G of t is the same as g of minus t. Why? Because if I look at this guy, what it's saying is that, of course, it's a stationary process, alpha. So if what matters is the time difference. So I take 0 and t is g of t. But I can also say, let me take this as 0 and this as minus t. It's the same thing, right? So what g of t, which is this, is identical to taking this to be 0 and this to be minus t, because all I want is there to be a time difference of t. So I can say this is minus t, 0 and minus t, and then I can of course interchange them. So clearly this is equal to saying minus t 0, which means g of t is equal to g of minus t. And because that is true, integral 0 to infinity g of t must be equal to minus infinity to 0, right? Because this is the same as that if I flip the t to minus t. Right? And so this must both be half of the integral from minus infinity to plus infinity g of t. That's like an aside. So because we have that behavior, if I define integral 0 to infinity g of t as d, then minus infinity plus infinity is 2d. Okay. We will later use this fact to recover what we want, okay, in the white noise limit. So the autocorrelation, those of you all who have done some work on some other courses may recognize from Green-Kubo formula that the autocorrelation relates to diffusion and so on. So that's why the d is coming here. We'll see it later more carefully. Okay, but for now, it's just a way of saying that I'm taking a nice, well-behaved stochastic process alpha, whose integral under the curve is fixed, right? And I'm going to call d. And then as I take this limit, while keeping this integral fixed, this entire g of this effective autocorrelation function of my zeta is going to collapse into a delta function, but such that its integral remains finite. That's why it has to become a delta function. Okay, and so therefore, if I take the limit now, so this is what I'm after, right? I basically want to say I have a zeta of epsilon. I want to see what happens as epsilon goes to 0. Okay. Clearly, the average of zeta epsilon is always going to be 0 because I'm basing it on this alpha whose mean is 0. So it's a 0 mean process. Right? But what happens to its autocorrelation as epsilon goes to 0? So based on what I've written here, I'm going to get 1 by epsilon square, right? G of t minus t prime, remember only the difference matters, by epsilon square. Okay, so it's just this multiplied 2 times and then I'm using this definition there. I just substitute zeta epsilon from here, right? So I'll get 1 by epsilon square, and then I'll get the autocorrelation of alpha, right? Where instead of t, I have this t minus t prime by epsilon square, right? That's all. Okay, so now I know this function, right? That is just this function g. But remember the argument now is divided by epsilon square. So as epsilon square goes to 0, this curve will shrink. Right? That is what I wanted. Okay. And so now you can see that, so let's do an exercise. Right? If t is not equal to t prime, then I'm sitting somewhere here, right, at some finite value. And as epsilon square goes to 0, that effective coordinate will go off. So I'll just get 0, right? So I'll get 0 as the answer. Okay, because I'll get g of infinity, and g of infinity on this thing is obviously 0, because I'm taking some process which is decorrelated. So for any t not equal to t prime, I will be looking at g at some very, very large time, right? Time as epsilon goes to 0, so that autocorrelation will go to 0. Right? But if t is equal to t prime, right, then I'll immediately get g of 0 by epsilon square. Right? This g of 0 will, right, behave properly. So that I am shrinking off, right? So I will get something going off to infinity. So it's going to behave like a Dirac delta. That is the point, right? So this whole function for any non-zero, whenever t is not equal to t prime, I'll get 0. But when t is equal to t prime, I'm going to get infinity. That's like white noise. So I'll get a Dirac delta, but multiplied by my 2D guy here. Okay, because I wanted to reproduce the correct area. I could have chosen some alpha which is suitably normalized so that the autocorrelation is 1. In that case, I'll just get the Dirac delta. Okay, but I'm leaving that d over there. So in this sense, I'm going to get the white noise. I mean, that is the precise way I get the white noise limit, okay, as epsilon goes to 0. So it is I'm approaching that limit based on some well-behaved stochastic process just by rescaling that time. Okay, so if this discussion is a little confusing, it will become clearer when we look at it in terms of the ODE and its complementary process for alpha. Okay, so we'll come to that in a second. But I just want you to see that we have formulated in a way that is consistent with what we have done for the beginning. Okay, so if I have some variable x, it's some dynamical system that I want to study, and I want to include the effect of some fluctuating forcing. So it could be, for example, the effect of turbulence, turbulent mixing or turbulent drag or something on your system. So imagine you have a ball sitting in a flow. Right? You can say the force on the ball is Stokes drag, but now the flow is also turbulent, so the force will fluctuate on the ball. Since the ball just sitting there and moving with the flow, it will also have some fluctuation because the flow is turbulent. And you want to model this somehow, and you have some model for the effect of the flow. Right? So one way of doing it in the Langevin sense is to say, okay, I have the normal deterministic part of the force, which you know from your usual theories, plus I add some noise, okay, which you are modeling in some way, but the noise is correlated because in the end, whatever physical process you're putting in has some finite correlation. And this coefficient comes from the physics of the problem, right? It depends on how you put in the forcing, how it is affecting the variable x. So this B is coming again from just modeling the macroscopic stuff. This B has nothing to do with the small scale fast process. Okay, so for example, if I have this force on the ball, right, then the effect of fluctuations will be directly felt. Maybe B can be said to be some constant. But on the other hand, if you think about, let's say, a flow over a surface, and then there are turbulent fluctuations, the force experienced by the surface depends on the shape of the surface. And I want to solve for the shape of the surface. Right? So obviously, if I have a flat surface, air over it will affect it differently than if the surface is deformed. So in that way, noise in the wind will affect the surface in a way that depends on the surface shape. Right? So that's what this B being a function of x really represents. Right? So it can be multiplicative in many problems. It's just saying that the noise you introduced, right, the correlated noise you introduced, will have an impact on your variable to an extent that depends on the variable itself, which is true of many kinds of problems. Okay. So that's all I'm starting with, right, in the Langevin equation. And now I'm saying, okay, I don't want to really specify the correlated details of that process. Right? I don't know what they are. And I want to get the simplified version of when all I'm going to say is those fluctuations are much, much faster. Okay, but I approach that limit in a way that at all times I'm finite, and then I take the limit, right? Because in reality it really has some correlation time, it's just that it is small. So that's what we are doing here. Okay, because I'm starting with this right now for any epsilon is some nice correlated process with some autocorrelation function. Right? But as epsilon goes to 0, that function gets more and more singular, more and more like a Dirac delta, and in the end I will get a Dirac delta. So the epsilon tending to 0 limit is white noise. Then this zeta 0 is exactly like how Langevin took white noise with infinite variance and 0 mean. And then the question is, I have B, I have white noise. Right? What we have said so far in the course is the correct way is you rewrite this as an SD. dx will be A dt plus B dw. But the problem is, what should I do with the multiplication? Is it Ito or is it Stratonovich? Right? If B is constant, I would have no problem. That's why at the beginning of the course, B was constant, because we did just normal random walk, right? Where this B was 1. So then I just did dw, right? And then you can have simple arguments to justify that from center limit theorem and random walk theory, right? But when B is a function of x, it's not obvious what to do. Okay, so that's what we want to do. So let's just look at a preview, right? So we will now show right this 1 So what we will show at the end of the next couple of lectures is as we take epsilon to 0 there, right, equation 1 will converge in the weak sense, I'll come back to that again, right, to the following SD. Okay, so that zeta epsilon will become zeta naught, which is white noise, and we already know that that is a singular way of writing it. The correct way is to rewrite it as an SD, where instead of the white noise, you will have the Wiener increments, which are defined for any finite discretization dt. So I'll get dw. The key point of the whole derivation, the new thing, is to show that this will not be Ito, but it will be Stratonovich. And we are going to do this with one restriction. Okay, we are going to require alpha of t on which I am basing, right, this zeta to be a Markov process. Right? Only in that limit I will be able to prove this. Okay, but that's not a big restriction, because remember what we are trying to do is we are trying to model the effect of some unknown rapidly fluctuating process on x. Okay? So as long as I say, okay, the forcing that I am introducing is a Markov process, that means I have to have some way of generating this zeta of epsilon, right, which is anyway something I have cooked up to add to the model. So this zeta of epsilon, in taking the limit, is really related to this alpha. So I am cooking up this signal alpha, just making it fluctuate faster and faster by introducing the time scale ratio epsilon. Okay? So the thing I am really generating is alpha. Right? That is just something I generated randomly. So as long as I decide to generate alpha, right, through some process that will make it Markovian, then whatever I do next will be fine. Okay? So that just means that the alpha that I get at the next time only depends on what's happening now. Right? I don't create some process that depends on what alpha was several time steps before or something like this. There are some generalizations of what I'm going to do here, but those things are discussed in Gardner's book. But for us, this is fine. Okay. So what does this mean? To be more precise, right? That if I have this alpha in this way, it really means that alpha itself can be written in terms of some SD. Okay. So the alpha itself I can generate, right? Okay, how do I know that I can write it like this? So in practice, maybe I generate alpha not using any SD, right? So for example, in the smooth random noise, I'm not generating alpha in this way, right? I'm using some Fourier series or whatever. Right? Or I could use some kind of computational algorithm to toss random numbers and do various things, right? And get this alpha, which can be Markovian. Markovian just means that then alpha the next time is either completely independent, right? Or it just depends on the current time. So in fact, a simple way to create a correlated random time series alpha, one I showed you in terms of Fourier series, right? The other way is to say, okay, I have a value of alpha now. For the next time step, I toss a random number. And the value I choose for the next time step is some linear combination of what I have now and the random number. Okay, so if I take the linear combination as being fully the new random number, it's just the Wiener process, completely delta, uncorrelated, okay, at the next time step. But if I say it's a combination of what I had before and the new number I generated, it is obviously correlated to the previous thing. So it's a simple way to create a correlated time series from a completely random delta correlated time series. Okay, so again, this is not satisfying any particular SD in the sense that I'm not generating it using an SD. But I'm saying regardless of that, as long as alpha is a Markov process, I can always say that it is the solution of some SD. I may or may not be able to write this down easily, but I can be sure this happens. Can you tell me why? At least the statistics will be reproduced. So you go back to our early lectures on continuous Markov processes, right? We started first with that before we came to SD. And there we said that if you have a Markov process, it has a corresponding Fokker-Planck equation. This is what we proved before talking about SDs and so on. We just said that if the process is Markov and is continuous, so I should add continuous Markov process. Right? As long as you have some continuous Markov process, it will correspond to some Fokker-Planck equation, right? At least for its statistics. And then that Fokker-Planck equation, I can always write a corresponding SD, Ito SD. Okay, so based on that, we know that, okay, for sure, whatever this alpha is, however you cooked it up, as long as it's continuous Markov process, I will have a corresponding SD. I'm just writing the drift and the fluctuating terms with some capital A, capital B, right, to distinguish it from these guys. And I don't need to know what these are, and I will not need to know them later on also, as you will see. Okay. Now, does this have to be Ito? It doesn't have to be. It could be Stratinovich. I can always convert it to Ito, right? So that is a material. And in the end, I'm not going to have to specify these things. What's important is that I can write it in this form. Okay, so now that we have formulated it this way, really what I'm doing is I'm saying I'm starting with a dynamical system which has two equations, right? One ODE and one SD. And I want to somehow get rid of that SD in the limit of epsilon going to 0. And this limiting procedure we will cast, right, as a center manifold problem. That is how the connection will appear. Okay. So let's just, what is missing now is I have this equation, right? And I have that equation for alpha, but I don't see the epsilon in that equation, right? So that alpha is just for this nice process, but I need to now rescale it with epsilon, and I want to write it in a way that connects directly to this dynamical system. So we'll just rewrite the two equations together. So we now have a random, right, random dynamical system. Right, so I'll just copy the X equation as before, but introducing alpha. Let's remember zeta of epsilon was 1 by epsilon alpha of, I put t by epsilon square in the earlier discussion to explicitly show you that alpha of t is some nice signal, but when I replace its time argument by t by epsilon square, I can make it go to white noise. Now I don't need to do that because I'm going to write the equation for alpha. So as an SD. So when I do this, I'm going to leave alpha, I should leave alpha as it is here because it's like a variable. And I'm going to write another equation for alpha. That equation should be scaled in such a way that its dynamics are much faster. That's the natural way of doing it. So I will now have an equation for alpha, but this is an SD. It is not an OD. Did I write A of alpha there or A of X? Yeah, alpha. Right, because this SD has nothing to do with X. At least that's what we're assuming for now. Okay, some E2 SD. So now these are two equations, one-way coupled, right? Because alpha has nothing to do with X, is just some rapidly fluctuating stationary Markov process, and I'm using that to force the X equation. Now, at the way I've written it here is just saying that as epsilon goes to 0, alpha becomes huge. It's not giving me the fact that it's fluctuating faster and faster. Because earlier I had put t by epsilon square. But here it doesn't make sense to divide the argument. What I should do is scale these coefficients in such a way that the dynamics of alpha are that much faster. Okay. So recall that epsilon was used as the ratio of, epsilon square was used as the ratio of time scales. Okay. So really if I think of this as a separate equation in terms of some dt prime, right, this would be fine. But now I want t prime to be epsilon square compared to t, right? The ratio of the scales should be such. So if I rescale the problem to bring it in this time scale, I'll get epsilons popping out. Right? That's what would happen in usual scaling. And because this goes like dt, I should get a 1 by epsilon square here. Okay. And remember dw goes as root t, right? So I should get a 1 by epsilon here. So that's why I introduced epsilon square as the ratio of time scales, so that when I get the root of the time scales, I would get epsilon. But of course, if you didn't do that, you would have epsilon, root epsilon, doesn't matter. Okay, so another way of thinking about that is that the coefficients are large. Right? As epsilon goes to 0, the coefficients that drive the dynamics of alpha are much, much larger than the corresponding coefficients in X. That's why the dynamics of alpha is much, much faster. And this epsilon square, epsilon and so on just gives me the correct scaling. So that in terms of the time variable t, this dynamics are 1 by epsilon square faster, if you like. So the epsilon goes to 0, they are that much faster. And then this 1 by epsilon corrects for the amplitude with that root t behavior so that the white noise does not go to 0 but gives me a finite contribution. Right? I mean, otherwise, this term will not be white noise. Right? It will just become 0 in the mean, in terms of its effect. Okay, is this clear? Okay, so the other way I could say this is I would say, okay, let's scale this with some time, characteristic time tc. This has some other characteristic time tau, right? Then I would, when I rescale the time, non-dimensional t by tau will come here, correct? Or sorry, this is non-dimensional t, the tau will pop outside, right? Here I'll get root tau because of the behavior of the Wiener process. And now I just have to realize that this tau by the Tc there is related via epsilon square. Okay. And so that ratio will come out. That's all. It's just like scaling it with two different time scales and setting that ratio to epsilon square. Okay, very good. So now this is a consistent two-dimensional random dynamical system, okay, with one-way coupling. One is an OD and one is an SD. And you can see that as long as epsilon is finite, this will remain an OD. Nothing funny about it. The problem is when epsilon goes to 0. Right? Then the singular behavior is clear. This will go off to infinity. And these terms will also go off to infinity, rapidly fluctuate. Okay? And what I want to do is get an effective equation only for x by eliminating the alpha and replacing it somehow by noise. Okay? Now, how this fits into center manifold is not clear, right? Because of this Wiener process and the SD behavior. Okay? So how do we bring this into the world of center manifold, right, mathematically? Because physically we can see it's very similar, right? I have a slow variable, right? I have a fast variable, right? Because of this scaling. As epsilon goes to 0, this will become faster and faster compared to the slow guy. So I should be able to do some kind of center manifold reduction where I write alpha as a function of x and so on. Right? The problem is this, I don't know what to do with this Wiener process. Right? The usual dynamical systems theory I know doesn't apply. So what we will do now is move from the world of SDs to the Fokker-Planck equation. Right? Because that's the standard way of going from, right, fluctuating stuff to something now deterministic. Right? But you'll get a PD. So where I have some kind of random ODs, right, where I have to deal with the randomness. If I go to the probability density world, right, I will get a deterministic equation for its evolution, where the effect of noise comes in like diffusion, but I will now end up with a PD. But I know how to deal with that. Right? Remember, we've already done center manifold reduction for the Taylor-Harris problem, which you dealt with the PD. So let's do that now. Okay, so we will now consider the probability distribution, right? But remember, what are my coordinates now for the probability space? It's not only x. Right? So x is a random variable because of its dependence on this fluctuating alpha, and alpha is also a random variable. Right? So I have a two-dimensional probability space, x and alpha. Right? Alpha is a random variable, and because of alpha, x is also becoming random. So I need to consider the probability density in the coordinates x and alpha at some time t, right? Given some initial condition at 0. So I'm going to consider the evolution of this conditional probability distribution, for which I can write a Fokker-Planck equation. Right? Because I have said that alpha is a Markov process, and because it's a Markov process influencing x, x is also Markov. Right? So the two-dimensional dynamical system is a one big Markov process, for which I can write the Fokker-Planck equation. Right? So how do we do that? Again, recall your earlier classes, because we know the SD, we just write it down by inspection, right? The drift terms come into advective-like terms, right? D by dx. This whole thing is a drift, right? There is no noise in x right now. Remember, as long as epsilon is not 0, this is just some other, it's like another drift term, right? It's not, there's no dw here. Right? So this whole thing is a drift in x. So you'll have d by dx of this drift into the p. In this equation for alpha, there is a drift, right? Multiplying by dt. Because if I take d to the other side, all of this gets multiplied by dt. So this whole thing is drift. Here the drift term is this a by epsilon square. The noise term is b by epsilon, which will come, remember, in the diffusion-like term, but now in alpha. Right? So the diffusion will act in the alpha coordinate. So let's write that down. So I'll get dp by dt. So let's start with these terms. I'll have a minus d by d alpha, right? The drift in alpha, right, of the drift coefficient. So I'll have a by epsilon square times p. Okay. And then I'll have plus, now this will come in the diffusion term, and it's an Ito equation, right? So I will just have half dou square by dou alpha square times this squared, right? Remember the Fokker-Planck equation, the drift and the effective diffusion coefficient sit inside the derivatives. Okay, so this is coming from the alpha equation. Now I have a drift on the x, right? So again this minus again comes from the Fokker-Planck equation, right? You have minus d by dx of the drift term. So I have one drift which involves this thing. So I have small b alpha by epsilon, b alpha by epsilon, right? There's a drift times p. And then another term, I'm just separating it out because this has epsilon, that doesn't have epsilon, right? AP. Okay, so that's the multidimensional Fokker-Planck because I have this x and alpha dynamical variables. Okay, so this you can just write down by inspection. And so now you see it has this interesting form. If I separate out the terms with different epsilons, okay, so I can write it in the following linear operator form. This whole thing, first of all, is a linear equation. It's a Fokker-Planck equation, right? And so I can think of it as different linear operators. And I'm doing this, of course, because I soon want to use center manifold stuff. So you can see that I have the 1 by epsilon square terms, which are the biggest terms. Then I have some 1 by epsilon terms. Then I have some term without epsilon. Right? And I've called them L1, L2, L3. So the L1 operator is just the Fokker-Planck equation acting only on alpha. So anyway, that is independent of x. Right? And so you see that I have the drift and the diffusion, the A sitting inside the derivative. Right? So the way I write it is L1 as an operator acting on P. So when it acts, the P will come here. Right? The P will come there. Okay, so that is the L1 operator, which is divided by epsilon square. The L2 operator is this minus d by dx, where I have B alpha, which will multiply P inside the derivative. And L3 just has A multiplying P. Okay, so now you see the beauty of this idea that we cast our, so what we did till here is just formulating in a precise way the question we had, right? That if I start with a ODE of the Langevin type, where I force with some correlated noise, how can I take the white noise limit systematically? The systematic way is to write it like this, provided the random function, correlated random function you're using is generated by a Markov process. Then you can write it like this. Now as epsilon goes to 0, the random process will get faster and faster relative to the slow variable, right? And eventually you will hit the white noise limit. Now how to take that limit, right? And how to get results? I can't do it like this, but if I only am interested in the statistics of x, right, then I can shift to the Fokker-Planck equation for the probability and density of x and alpha, because it's a 2D system. That's why I said what the derivation I'm doing will give you the Stratonovich SD in the weak sense, because the proof is going to be based on the Fokker-Planck equation, right? And remember, many different SDs can give you the same Fokker-Planck, only their statistics will be same. So individual trajectories of this system when epsilon goes to 0 will not coincide with the trajectories of the Stratonovich, but the statistics will. That's why I said weak sense, not strong sense. Fine. So the moment we come here, all results are in the weak sense. Fine. So we are coming here now to the probability distribution evolution, right? And then we can write down the Fokker-Planck by inspection, because this is just an Ito dynamical system. Now here we see that the epsilons come in a nice way, and we get the following thing. Okay. So this now has the classic behavior we need for our center manifold reduction, right? It's very similar to what we saw in the Taylor-Harris problem. So you have these epsilons sitting there. I could have also, if I rescaled, right, I would have had the, so here these terms are becoming big, right? If you rescale it in the usual center manifold way, you'll have these terms becoming small and this being order 1. It just depends on whether you go with the slow time scale or the fast time scale, okay? In the usual center manifold reduction, you scale with the slow time scale, right? So that the, you scale with the fast time scale. So the fast term is order 1 and the slow processes become small. If you scale with the slow time scale, the fast processes will have huge coefficients. I'm doing it this way because Gardner has done it this way, right? So just so that if you look at his book, you will recognize what I'm doing. But I discussed in the Taylor-Harris class how you can do either way. Finally, you will get the same answer, right? What's going to be important is when I take what happens in the limit epsilon going to 0. So you see here as epsilon goes to 0, because I can multiply through it by epsilon, you will see the only term that will survive is this L1p. Right? Just see that. What do I get? That's what happens when you scale with the slow time scale, right? If I scale with a fast time scale, that means that it's like saying multiply throughout by epsilon square. Okay, so I will get epsilon square here, L1p, epsilon square. Okay. Now this epsilon square, to go to the fast time scale, I will absorb into that new time. So I'll get t prime, which is fast. So it will be dp by dt prime is equal to L1p plus epsilon this plus epsilon square this. When I put epsilon to 0, those two will knock out. Instead of getting this, I will get dp by dt prime equal to L1p. Fine. And then I should ask, does this have a slow manifold? Right? Does it have a 0 eigenvalue direction? Is L1 singular? If it is singular, that means the problem has one direction where nothing is evolving. And I can use that to build the slow manifold, as I discussed in the earlier class. So that is the proper center manifold reduction. If I were to do it my way, I would rewrite this thing. Right? This is equivalent to right, where I have so epsilon right, so I would have got epsilon square here, and then I can absorb that if I write t by epsilon as t prime square, sorry. No, so just as a rescaling. So if I rescale the problem, I would have gotten this. So if I see this, the moment I see this, I should ask, L1 is like, remember it's an operator, right? If you discretize the, so L1 is acting in alpha, right? If I discretize alpha direction of this PD, I'll get some matrix. And the center manifold theory will immediately say, what are the eigenvalues of L1, right? If they're all negative, then everything is evolving quickly. There is no center direction, right? But if L1 has a 0 eigenvalue in this limit, then when epsilon is finite, it means that smoothly continuing from that direction or using that direction as a coordinate, I can build the slow manifold on which all the fast dynamics will collapse. Okay. So even when I find this, my first question will be, does L1 have a null space? Okay. And the other way of doing it, which is what I've done here, right? Scale with the slow time, putting epsilon to 0 in some kind of like a perturbation theory will give me this problem, L1p equal to 0. And again, I will directly encounter the fact of whether P has a null space. Right? If it doesn't have a null space, P will just be 0 at leading order. Right? But if P has a null space, then only P is non-zero as epsilon goes to 0, and that's what we expect. So in either way, the question is, Does L1 have a null space? And if it does, then immediately the whole problem is cast into the light of the center manifold or Lyapunov-Schmidt reduction, right, which we did for the Taylor-Harris problem. There's no difference between, I will come back to the direct connections in a second, but it's just some PDE, right, which has two directions, right, x and alpha, and we can see that with some parameter epsilon, and when epsilon goes to 0, you find that the problem has a null space. In other words, there will be a slow manifold that is waiting to be constructed, such that when epsilon is small, the dynamics, instead of living in the full alpha x space, will collapse to some reduced subspace. Okay. Fine. So does L1 have a null space? Let's think about that for a second. Okay. So anyone, do we think L1 has a null space for any? So remember, L1 is what, right? L1 is this thing, where capital A, capital B are based on how I am going to create this alpha process. And I said I don't want to specify that, right? It should not matter. In the end, I'm going to take the white noise limit, and the only thing that will matter is the variance of that process in the capital D. Because when you specify some white noise, you don't have to say anything. You just say it is delta correlated. It has infinite variance. That means it's a Dirac delta. Maximum, you can multiply the Dirac delta with something so that you control the area under the curve. That I choose as D. So in the finite, if I look at it forward, and I'm going to replace alpha by white noise, right, I should not have to specify anything. But it looks a priori here that it seems like whether L1 has a null space or not should depend on this stuff. But can you think about why you can say whether, can you answer this question regardless of A and B is my question. So notice that in the Taylor-Harris problem, we could always immediately say it had a null space. Why? Because there the equivalent of this operator L1 was just d square by dr square, or 1 by r d by dr, right, r square c equal to 0. That was just because of cylindrical coordinates. If I was in Cartesian, it would be d square by dy square c equal to 0. And immediately it's clear to me that c equal to constant is a null space. So as long as I had either periodic boundary conditions or no flux boundary conditions, I know I have a null space, right? Because any constant was obviously a solution to the equation. So here the question is, do I have some solution? Are there functions p such that L1p equal to 0? And it may seem like to be able to say that I need to know what a and b square are. Of course, what the function is definitely depends on what a and b square are, right? But does even that exist or not? One may think that it depends on a and b square. So can you tell me why you can be sure that there is some p, right? In fact, a unique p, and not only some. It's not that it's multidimensional. There's only one p. That's even stronger, right? So there's only one function p, modulo a constant, which will take L1p to 0. Right, so obviously if L1 is some arbitrary operator, you cannot say this. But remember, what is L1, right? L1 is coming ultimately as a Fokker-Planck equation for the alpha process. So if I forgot about x for the moment, this is a closed SD in itself. I can write the Fokker-Planck equation for this. Right? So that would be looking at just this guy, right? Evolution of p of alpha comma t. The Fokker-Planck equation is just these two terms. That is L1. So the Fokker-Planck equation for the alpha process is dp by dt is equal to L1p. So now can you tell me from this idea why you know that there will be some p for which L1p is 0? What would that correspond to? Suppose you know the p such that L1p is 0, what would that mean in terms of the Fokker-Planck for alpha? Right? Let me say this, right? That's what I'm trying to say, right? So if you just think of the alpha process by itself, which is independent of x, you can write this. So what is now, suppose L1p was 0, what does that mean for the, what is that p? What is the implication, right? If I have the Fokker-Planck equation, what is the implication of the probability distribution such that d by dt of the probability distribution is 0 here? What distribution is that? And are you guaranteed to have such a distribution? It's a distribution of the stationary process, right? So I have some right, SD for alpha. The whole basis of this is that I'm looking at this problem when alpha has reached stationarity, right? So I have some process alpha. It is now stationary. That means the statistics don't evolve in time anymore. Then I'm using it to force the X equation. That's why I looked at the autocorrelation and said autocorrelation only depends on the time interval. Right? Otherwise, I can't do that. So the whole premise is that I'm looking at some stochastic process alpha, which is stationary, and using it to force X. That's why I looked at the autocorrelation being a function of only the time interval and so on. This means that alpha does have a stationary distribution. That is like my basic assumption. And what will that stationary distribution satisfy? It will satisfy the Fokker-Planck equation where dp dt is 0, right? That's the definition of being stationary. If it is not stationary, then the statistics of alpha are evolving in time. Correct? So because of this, right? Right, hence I will have L1 PS equal to 0. Which is only a function of alpha, right? Is the stationary distribution. Okay, so that's the key idea, that it's not some general operator, right, L1. It is a Fokker-Planck operator. Right? That means it governs the probability distribution of this alpha. And because I know that I'm going to look at alpha which has a stationary distribution, right, that corresponding PDF of alpha when it is at stationarity will definitely be the null space of L1. Okay. Right, therefore, the kernel of L1 is not empty. Right? It is spanned by PS. Now, of course, in terms of actual PS, I will normalize it so that integral of PS is 1. Right? But in terms of general operator theory, any constant multiplying PS is also a null space. Right? So PS just spans the kernel. But I know it's also one-dimensional because there will be some unique stationary distribution of alpha. It is not that I'm going to have multi-dimensional null space. That's because of what alpha is. Right? It's a Fokker-Planck operator of the stationary process alpha. Right? If it was some generic PD I write, then I have no idea what L1 will do. So throughout, we're going to use this fact again and again. Right? That we have started with some PD which has timescale separation, but the operators in that PD are really true Fokker-Planck operators. Right? So then, without knowing A and B, I can say certain things. And I'm going to use that fact to ultimately derive the result without specifying capital A and capital B. Otherwise, there's no point of the derivation. Right? So the first place I'm going to use this fact is right here to recognize that the L1 will have a null space spanned by the stationary distribution of alpha. Okay, and that's the key thing I need to do my center manifold reduction. Right? I know now I have this null space spanned by one function. Right? And then if you go back to center manifold reduction, this is great. I have this null space. So what I need to do now, I need to project my P, which is the variable, right, onto the null space complement. Then I take the whole equation and I should project it onto the range of L and the range complement, right? And then I will split up the thing. I'll ultimately be able to get a one-dimensional. One-dimensional means in this case I will get rid of the alpha dimension. I'll only get an equation for X. That would be a Fokker-Planck equation for X with some extra terms coming from this stuff, right? And the beauty is those extra terms, when I reinterpret as an SD and X, will bring out the Stratonovich. That's how we're going to see this working out. Okay. So the one ingredient I already have, right? At this point, I know that I can do center manifold. To actually do it, I need to find what is the range complement. Is that PS or is that some other function? That is related to whether this L1 is self-adjoint or not. That we'll do in the next class probably. Okay. Already you can recognize that for the usual diffusion equation is self-adjoint, but this is not the usual diffusion operator because the drift and diffusion coefficient are sitting inside the derivative, right? If it was a usual space-dependent diffusivity, B should have been nested between alpha, d by d alpha, B d by d. That would be self-adjoint. This is not self-adjoint. So if we do integration by parts, blah, blah, in the next class, we'll see that we'll get a different operator, L1 star, whose null space is the range complement of L1. We'll see that in the next class. That also has some interesting connections to what I've taught you before. But let's pause here and just, I want to highlight now the connection between that Fokker-Planck equation, multidimensional one, which we are trying to apply center manifold reduction to, and the Taylor-Harris problem. Okay. Because from that, you'll immediately see where we're headed. So let me call this equation 2. Okay, so what I want to say, alpha is like the transverse direction, right, in which the diffusion is fast. So in the Taylor-Harris problem, we did it in a pipe, right? So we said the radial direction is short, so the diffusion is very fast there. It will homogenize things so that C may not be constant in R, but it will reach some kind of smooth distribution very rapidly. What that is will come from the center manifold, right? But we know that things will rapidly evolve and collapse in terms of R variations. So I can average out the R direction. That was the physical logic. You see the same thing is there here, right? Alpha is like the transverse direction, right? If X, I have a PD and alpha and an X. X is like the slow advective direction, right? In which, so in the pipe, remember X was the slow direction along things which were advecting slowly, and alpha you can think of as the fast radial direction or transverse direction. In that Taylor-Harris problem, there was only diffusion, and it was physical diffusion. So if B was space dependent, it would be nested in the derivatives, right? It's a different kind of diffusion operator, but nonetheless, you can see it's like you have diffusion in alpha, which is rapid because I have the 1 by epsilon square. Right? So it's fast diffusion in alpha. In addition, I have some kind of advection also. Fine. Okay, but I have fast dynamics in alpha, slow dynamics in X. That's like Taylor-Harris problem where I had fast diffusion in R or whatever transfer direction you have, and slow advection in X. Okay, that's the first point. Second point, the drift velocity in X, right, is what? B alpha, right? So of course it's B alpha plus A, okay. Right? It depends on alpha. That is just like U of R being some mean, right, in the Taylor-Harris problem. Right, so I think of R as a transfer direction now. You see, not only is alpha like the radial coordinate where there is some fast diffusive dominated process. Right? Here, even though I have advection, there is also the diffusion. Right? So advective diffusion doesn't matter. Some fast mixing is happening in the alpha direction because of diffusion. And secondly, now if I look at the X direction slow process, why does X direction care about what's happening in the rapid R direction in Taylor-Harris? Because the velocity that's driving things in the X direction depends on R. Right? The velocity had a parabolic profile. If the velocity is a plug, then who cares about the R direction? You directly do plug flow reactor. Right? It's because the velocity is parabolic, that's why some things move faster, some things move slower, and then I need to see about how things are mixing in R. So the same thing is happening here, right? It's because the drift in X is A plus B alpha. So the drift depends linearly on alpha. Therefore, I need to, that's what's coupling the fast and slow directions, right? So just like in Taylor-Harris, my effective velocity in the X direction depends on the fast coordinate, depends on alpha. And it's this varying drift when you average out alpha, which gives you effective diffusion. Same thing happens in Taylor-Harris problem. There you call it Taylor-Harris dispersion. Right? So the signal in X, if I take a pulse in X, As it moves, it spreads, right, like a Gaussian. That spreading is coming from the effective diffusion behavior that is really being driven by u of being a function of r. The same thing will happen here now, that's what we're after. That in the end, I'm going to eliminate the alpha direction by doing center manifold reduction. This will go off. And this alpha here will get averaged out somehow. So I don't know what alpha to put here, right? There are many different values. I will somehow have to, when I average out this alpha, depending on A and B and this PS and so on, I will get a mean alpha to be put there. That mean alpha will turn out to be a function of how P depends on X and so on, and you will get this advection which depends on alpha will become diffusion in X. Right? So just like the Taylor-Harris problem gave us a new diffusion term in X, here the center manifold reduction will give us a new diffusion term in X. So I'll get a Fokker-Planck equation only in terms of X with an extra diffusion term. And when I reinterpret it as an SD, that effective diffusion term will give me the Wiener process white noise Brownian term. The question is whether the diffusion term will be like Ito or Stratonovich. Right? It turns out that it will have the Stratonovich form with the, this is the Ito form. Stratonovich form, remember, has a nested derivatives, right? It will give me the nested derivatives with the small b. And then I will be able to rewrite this as B circle dW. So this is just an anticipation. You can already see the calculation will work out because at this point it's almost the same, it really is the same problem as Taylor-Harris. Only the difference is in the operator. Right? In the Taylor-Harris problem, okay, it didn't have the drift, but more importantly, you see the derivatives are sitting inside. In the Taylor-Harris problem, it was constant. Or it was sitting outside, if you like. Right? So if suppose this B was outside, A was outside, then P equal to constant will be the null space. That's what happened in the Taylor-Harris problem. Here, because it's sitting inside, that's not the null space. Instead, the null space is this stationary distribution, which is not a constant. So there's some varying function of alpha is the null space simply because right, the derivatives are sitting inside. So if I put constant, this is not 0. I need to have some PS which is varying in such a way that it becomes 0. But I know that PS exists, right? Because I know the stationary distribution exists. So we'll build on this. There will be some differences in the calculation precisely because this L1 doesn't have a null space which is just a constant. It has some PS span null space. Moreover, we'll see L1 is not self-adjoint. So these things will introduce some nuances, but really the calculation is the same. Even physically, it's going to do the same thing. Right? The varying drift, a drift that varies in the fast direction, when you average out, will give you a diffusion in the slow direction. That diffusion will ultimately be a Wiener process Stratonovich term in the SD. Okay, so let's stop here. Okay, we will complete the calculation on Thursday, and then we will. So ultimately, we will prove what I showed. We're going to prove right in 1D. But then we will have some discussion about the multidimensional version, where you will see something interesting happening. Okay, so we'll pause here and meet on the next class.